Welcome to section 7.2, Statistics and Sampling Distributions. In this section, we'll explore how sample statistics, like the mean or sample median, vary across repeated samples. This variation isn't random noise. It follows a pattern we can model and understand. These patterns, called sampling distributions, are the foundation for much of what we'll do in inference, confidence intervals, hypothesis tests, and more. Understanding them is like knowing how your car handles under different conditions. It's how you drive statistics with control. Imagine you're trying to estimate how much students at your college sleep on weeknights. You take a sample and calculate a mean of 6.2 hours. Another group does the same thing and gets 6.8 hours. Which one is correct? The truth is, both are expected. When we sample, our results will vary. But this variation itself follows a predictable pattern. That's the sampling distribution. This distribution tells us how much our sample statistics bounce around from sample to sample and whether our results are consistent or extreme. Without this framework, we can't tell if what we found is typical or surprising. Let's define it more clearly. A sampling distribution is the distribution of a statistic, like the sample mean, median, or proportion, over all possible samples of the same size from the same population. If you took every possible random sample of size 10 from a population and calculated the sample mean each time, then lined up those results on a number line, what you'd get is the sampling distribution of the sample mean. It's like watching 1,000 simulated games of Mario Kart. You don't just see one result, you see how often each result occurs, which helps you estimate the odds of winning, losing, or landing somewhere in between. Let's visualize this with a simulation. Let's say we have a population whose mean is really 100 and standard deviation is 15. If I pick a sample size of 10, let's say I randomly sample 10 people, just one sample, I'm going to get one sample mean. And notice it's fairly close to 100. That's probably to be expected. But let's add in 9 more samples. So we have a total of 10 samples. We see a little more variation. Some have of our samples, one of them has a mean below 100. 5 of them just below 100, 1 just above 100, and 3 of them a little bit more than above 100. As I increase the number of samples that I draw, let's add 50 more, so we have 60 samples. It starts to look more and more like a normal curve, right? Our sampled values span the range, but when we calculate the mean, it's tightly clustered around 100, following that normal bell-shaped curve. So we would expect to occasionally draw a sample that has a mean down here at, what is that, maybe 80? And occasionally draw a sample that has a mean up here at 115. But most of our samples will have means somewhere between 95 and 105. There are 3 main ways to find or understand a sampling distribution. 1, a theoretical derivation. If you know the population distribution and the sampling method, you can sometimes calculate the sampling distribution exactly. 2, using a simulation. You can take thousands of random samples using software or Excel and compute this statistic for each one. The histogram of those values approximates the sampling distribution. Third way, 3, is the central limit theorem. For sample means, if the sample size is large enough, the distribution of sample means is approximately normal, no matter the population shape. In the real world, simulations are powerful teaching tools, But for actual inference, we often rely on the central limit theorem. Let's work through a simplified but powerful example. Imagine a very small population, the numbers 3, 6, 9, 12, and 15. Now draw all possible samples of size 3 without replacement. For each sample, calculate the sample mean and the median. This lets us build the complete sampling distribution for these statistics. Some values will show up more often. For example, a mean of 9 might be common, while others are rare. You'll notice that even with a tiny population, there's variability. Once we calculate all the sample means, we can build a histogram of them. This is the sampling distribution of the sample mean. We'll see that it clusters around the population mean, but not perfectly. Some sample means are lower, some are higher. And if we were to calculate the average of these sample means, it would actually equal the population mean. That's a huge idea. The sample mean is an unbiased estimator of the population mean. This concept helps us understand what's typical, what's unusual, and how much variation to expect in any research setting, from psychology experiments to marketing focus groups. So here's what we want to remember. Sample statistics vary from sample to sample. This variation is modeled by a sampling distribution. We can use theoretical math, simulation, or approximation to understand this distribution. Sampling distributions are how we estimate precision, bias, and likelihood, the foundation of inference. Whether you're estimating how long it takes Thor to recover after battle or polling students about an exam that they're stressing about, understanding sampling distribution helps you quantify uncertainty and make stronger decisions.